And let me introduce our next speaker, Daniel Ohm from SQRT. Daniel is a senior in the Department of Physics and Astronomy at Seoul National University. He is the lab member of Ashalom Group, led by Professor David Ashalom in the Pritzker School of Molecular Engineering at the University of Chicago. Daniel's research focuses on NV centers, condensed matter physics, and quantum benchmarking. Today, he will be presenting a talk titled Quantum Applications of NV Centers, sharing insights from the paper Towards a Room Temperature Solid-State Quantum Processor, the Nitrogen Vacancy Center in Diamond, Newman et al., and Microscopy of Magnetic Fields by Scanning Diamond Magnetometry, Welter et al. Please join me in welcoming Daniel to the stage.
Thank you for the kind introduction. As introduced, my name is Daniel Ohm, and I'm currently a visiting student at the Aushelm Lab at U Chicago. And I'm currently researching the platform of NV centers that refers to NV center defects in diamond. So I wanted to just give a short presentation on the quantum applications of NV centers, basically how they're made, how we can use them for applications such as sensing and quantum computing. And I wanted to cover NV centers because NV centers are kind of a niche platform in quantum computing, but they're the mainstream platform in quantum sensing. So I think it would be beneficial for everyone, those who are interested in quantum computing and sensing, to just get a gist out of this very promising and yet very old quantum platform. Okay, so basically what is an NV center? NV centers refer to defects in diamond, and the N refers to nitrogen, and the V refers to vacancy, which means nothing, basically, no atoms. So if you look on the slide, you can see a diamond right here. And instead of there being a carbon atom, we have a nitrogen atom. And where there was previously a carbon atom, we have a vacancy, basically a blank spot. So these are what we refer to as NV center defects. Now, if you think about the electronic structure of nitrogen and carbon, you'll soon realize that NV centers have basically three possible different charge states. They can be positively, negatively, or neutrally charged based on how many electrons I take away from the initial state. So now we're primarily interested in NV minus, basically negatively charged NV centers, because they have what's called spin triplet states. Basically, since they're negatively charged, they have an extra electron, which gives it three possible spin states, 1, 0, -1. And this is crucial for their applications. So the point of the NV center platform is to exploit this three spin state, basically quantum system, in order to perform quantum sensing or quantum computing. Now, if I ionize this, I get a neutrally charged defect, which only gives me a singlet state, which is not actually quite viable for any applications at all. So from now on, when I say NV centers, I'll be referring to the NV minus state. So how do we make NV centers? Yeah.
Could you please go back to the previous slide?
Yeah.
Okay, so how long is the lifetime of an NV center? Like, I guess that's not forever. The vacancies and nitrogens.
Are you referring to an optical lifetime or?
Yeah, I mean the vacancies, does they live forever or that?
Yes, they're basically permanent.
Permanent, okay.
Once you make them, for example, the sample I have in the lab was made in 2012, and we're still using it. Yeah, so they last a very long time. So they're basically stable at up to temperatures of 600 K.
Okay, and I have one more question. On the right figure, is that the NV minus?
Yes, this is the NV minus, basically. So the default is basically NV minus. And when you ionize this defect, you get the NV0 and NV plus. We'll see later on how you ionize them. So
okay. So and they're triplets because their total spin S is
yes,
1.
S is 1, yeah.
Yeah, okay, thank you.
Okay. So how do we make NV centers? Thanks for the question, by the way. So how do we make NV centers? Well, the most common method of making NV centers is basically called ion implantation. So for those unfamiliar, we grow diamonds in a lab using a technique called chemical vapor deposition, which basically means we start with a small amount of diamond and then we heat the chamber up to 900 degrees and just heat it up and put in some carbon gas, basically. So we heat up some carbon, make it into a gas, and put it in a chamber with some diamond seed. And what happens is that this chemical vapor, they latch on to the diamond seed, and they eventually grow into a stable crystal structure, which is the diamond crystal structure. So we basically grow diamonds starting from a small seed by letting carbon gas latch onto it. And so ion implantation actually implants these defects by a gun, basically, an ion gun. So this is a placeholder because I couldn't find a photo of an ion implantation device. Well, basically, we're taking ionized nitrogen gas and we're implanting them during this growth process. So basically, after we've grown these diamonds, we basically accelerate these ions into the structure and we let them collide with the structure. And when one of these nitrogen atoms, they successfully collide with a carbon atom, first, two things happen. First, the nitrogen atom takes the carbon atom's place. And then the second, basically, there are two, as you can see here, there are two atoms in a single, what do you call it, nitrogen gas molecule. One atom knocks the carbon out and takes its place, and another atom, which has a higher velocity, knocks the carbon and gets knocked itself out. So we have a nitrogen atom and a vacancy. So that's how we make NV centers. Now, this is the classical technique, but another technique you can use. Oh, wait, okay. This is the classical technique, but with this technique, there's a limitation to this technique, is that you cannot create thin layers, basically. This is really good for making localized NV centers, but they are really deep into the sample because they're so high velocity. So what do you do when you want to make a thin layer of NV centers, which is not deep into the bulk? So the technique you use is delta doping, which is a sample our lab is currently using. It's a technique our lab currently uses, is that during the heating process at CVD, instead of waiting for the diamond to grow and shooting it with ions, we instead disseminate neutral nitrogen gas into the chamber as it's heating up. So basically, as this diamond is forming, nitrogen is already in the chamber. And then after we let it seminate, the nitrogen latches onto the diamond seed along with the carbon atoms. And this also creates vacancies because nitrogen takes up a spot on the electronic structure and prevents a carbon atom from latching onto it, basically. Because, of course, nitrogen only needs 3 atoms. So it's preventing a carbon atom from taking place. But it creates these vacancies and the nitrogen. So vacancies are inherently positively charged, and the nitrogen atoms, they are negatively charged. So what happens when you heat them together? They start to move towards each other. So we have nitrogen defects with no vacancies, and we have just vacancies with no nitrogen. And they start to move towards each other as you start heating the sample up. And then that's how you get your NV centers. So this is a chart that basically compares the two techniques. So with ion implantation, you get really localized NV centers in a single place. So this is what you want to use when you want to make single NV center defects in a certain location. But what if I wanted to make lots of NV centers and create a thin layer of NV centers? This is when you would use delta doping. So localization is low for delta doping. You don't know where they are. You have to find them after you make them. But the thickness is very thin. So our sample has about 200 nanometers of diamond, and underneath of that, we have a thin layer of NV centers. It's about 2 nanometers. And the interaction range between the ion implantation delta doping is quite different between the spins, which makes it interesting to study. So for ion implantation, you can have very long range interactions because basically what you have is a 3D bulk layer of NV centers. So you have lots of different directions in which the NV centers can interact with each other. But for delta doping, what is really interesting is that the NV centers are only on a single layer. So basically, their interactions are in fact 2D, not 3D. So you have a 2D layer of NV centers, which only interact in somewhat out of plane, which is really interesting because what this creates essentially is not a 3D, but a 2D sample, a spin bath, a 2D spin bath. And so our lab was the first one to actually create such a sample. And actually, people have only been focused on single NV centers, so ion implantation, but not so much on delta doped diamond, which gives us 2D spin baths. So there are a lot of measurements and a lot of properties that we still don't know about delta doped diamond, and that's part of the research I'm currently doing at the Arshall lab. So one interesting thing that happens is that as you decrease the temperature, you would think the noise would decrease as well for delta doped diamond. It decreases for bulk. But for 2D spin baths, when you decrease the temperature, the overall noise actually goes up. So I made a measurement in the lab. So basically, in the lab, I made a measurement at 300K and 100K. But the 100K measurement actually more noisier than the 300K, which is because as you decrease the temperature for 2D spin bath, this is actually just a theory, but if you decrease, this is the current theory our lab actually is vouching for. As you decrease the temperature, you increase the 2D spin interactions. But since there are only two directions in which spins can interact, the overall noise doesn't actually dissipate. There's less direction for the noise to actually dissipate. So you have a larger concentration of spin noise as the temperature decreases, which you can see here through these graphs, the hand-echo 2D measurement. So basically for the left, this is the bulk, the right, this is delta doped. As you see for delta doped sample, it's much more noisier. Okay, so we covered NV-centered defect fabrication. So how do you actually utilize them in experimental settings? So the slide you see here is your quintessential NV center experiment setup. So there are three layers to this. The first is the camera, so you can see the sample, so you can align your laser towards the NV center. The second is what in the NV center nomenclature we like to call the excitation. You have two components, basically the laser and the microwave. The laser basically excites your electrons into a higher energy state. Your microwaves excites the spin states of those electrons. And the third component is called the collection, which is basically collecting the emission after you've applied your laser to your NV center. And these are typically comprised of photon counters. Okay. So once you got this experimental setup, what you do with these NV centers is you first do something that's called initialization. And then you do a processing sequence, which is different depending on what you want to do. If you want to do quantum sensing, there's a different processing sequence for sensing. If you want to do quantum computation, there's a separate sequence for that. And so once you do all of your operations, you finally read out using another laser pulse, which is typically the same wavelength as initialization pulse. So readout refers to reading out the spin state of your electron after the processing sequence. So what is initialization? Basically, in layman's terms, initialization can just be summed up as making sure I am in MS equals 0. Because of outside environmental factors, some of the spins may not be in MS equals 0. Sometimes you have cosmic rays hitting the sample, which excites the electrons into a different spin state. So what you want to do before you do anything else is you want to make sure your NV center is in MS equals 0. So what you do is you hit it with a laser. And so there are many different choices of laser wavelength you can use. So if you use a green laser, this is the safest choice. You get what's called complete excitation. So it's the safest bet if you want to do initialization. It's basically overshooting the energy you need to reach the higher energy state. So once you hit it with the laser, it goes up into the higher energy state, and then eventually decays depending on which spin state you initialize it was initially in. So if it was in +1, it would be it gets excited, and then it does something what's called intersystem crossing. which doesn't emit any photons, into what's called the singlet energy states. And then it decays, emitting some light. And then it decays back to zero state without emitting any light. If it was in a zero state, it just goes up and down. It decays optically fully. It doesn't do this ISC crossing at all. So the green laser basically does this process and it overshoots it. So it basically guarantees this process is bound to happen. Now, for more specialized applications, you might use what's called an orange laser, which is what's called the resonant ionization wavelength. This basically hits the NV center with light, but it also sometimes ionizes the NV minus state. So you have to be careful. So part of your NV minus actually turns into NV neutral once you hit it with an orange laser. So the reason for this is because this is the exact resonant ionization wavelength you need to ionize the NV center. So the final red wavelength is the resonant excitation, which is basically the resonant energy needed to do this transition from the 0 to the 0. And this only excites the NV minus because the NV minus is in a triplet state. So if I wanted to do an operation only on NV minus and not NV 0, I would use the red laser, basically in this case. And another word of caution is that pulse lengths shouldn't be too long or too short. For example, if I gave an orange laser and it took too long, some of the NV minus, all of the NV minus would turn to NV 0, basically. And I would basically be getting rid of all the defects I have. So for the next pulse sequence, another common pulse sequence is what's called continuous wave ODMR, which is basically asking, what are my transition frequencies? So when I explained the ISC earlier in this slide, when it was in this spin +1 or -1, it did what's called the intersystem crossing, which I mentioned didn't actually emit any light. But for the 0 state, it always emits light. So what would be brighter? The intersystem crossing state, right? So basically, by continuously applying my laser and continuously applying a microwave to excite my zeros into ones, I can find which frequencies actually excite my 0 into 1. Basically, if I keep tuning this frequency, I can use this to find the exact energy I need to turn my 0 into a plus or minus 1. So basically, this is what we're doing here, is we're trying to find these dips in the photoluminescence when the NV center actually decays. And these peaks tell me where these frequencies are. So what we typically do is do initialization. Then you do CW-ODMR to find the frequencies of the ±1. This is basically characterizing your system. And the final thing you would do is what's called the Rabi sequence. How long is my pi pulse supposed to be if I want to actually change my state from 0 to plus or minus 1? So as you know from basic quantum mechanics, as I apply this, if I apply a certain pulse again and again, it oscillates from the 0 to 1 state, which is called the Rabi oscillation. And we exploit this oscillation in order to find the exact time I need to transition my 0 into a +1. So CW-ODMR finds the frequencies, and the Rabi sequence finds time needed. So the final pulse sequence is called the readout. So, which is basically reading out the spin state, basically telling what the spin state is. So the readout is typically just using the same laser again, except this time our goal is not to initialize everything to ms equals 0, but it's to see what the final spin state was. And how we do this is by looking at the counts per time. So basically, if I have this peak up here, my initial state is ms equals 0. And if I have this characteristic ramp up, it's basically ms equals -1. And this contrast is due to the spin-dependent dark states I mentioned over here on the singlet energy levels. So this is an example of the pulse sequence, and this is actual data I took in the lab. And so as you can see, this is the ms equals 0 state we initialized. And here I applied a pi pulse right here. And this is the readout pulse. So after the readout pulse, once I do my initialization again, you notice this short ramp up because I was in the ms equals minus state due to my pi pulse right here. So what can you do with this basic platform? With this basic scheme, you can do what's called quantum sensing. So CW-ODMR is actually the basic form of quantum sensing I mentioned over here. And so the basic principle being, first, if I have an external B field, what would happen is that these degenerate plus and minus one states, they get what's called a Zeeman splitting. Basically, the energies diverge from each other, the stronger your magnetic field is. And I can use this to my advantage because the plus and minus one states are basically the locations of the peaks right here. So as you can see from this graph, as the magnetic fields increase, the locations of these peaks diverge from each other. So I use the locations, the divergence of these locations, to basically find out the magnetic field.
Okay,
So
I have a question.
yeah.
So you can only detect the strength of the magnetic fields? Like, can you detect its direction?
Yes, you can detect the direction, which is basically what this slide is actually explaining here.
Yeah, okay.
Because, well, the basic basic CW-ODMR is actually detecting the strength of the magnetic field across what's called the symmetry axis, which is this axis right here. So basically the axis where the NVC is located. This is the magnetic field it primarily detects. Okay. But using this, so basically, as you can see, this parallel component refers to the symmetry axis. And this perpendicular component represents the plane that's perpendicular to that axis right here. And as you can see here from this Hamiltonian, this is the perpendicular Hamiltonian. And in the interest of time, I'm not going to explain where we got this from. But we have these two components, D and E, which are called the zero field parameters, which characterize the Hamiltonian right here. So as I mentioned earlier, we assume mostly that this Hamiltonian is much greater because that's mostly the experimental setup you have. But instead, if I were to change the setup, if I were to rotate the setup, instead of having B and V, I would also have X and Y basically components right here. So basically by rotating my stage, I can measure different components of the BX and BY. So basically, yeah, you can measure different components. You just need to rotate you just basically need to rotate your sample around. So basically, yeah, to answer your question. So another form of magnetometry you can do is instead of continuous wave, wait, let me just see how much time I have left. It's been 30 minutes. Yeah, okay. Okay, I'm running out of time. So basically, yeah, I'm going to skip this because it's not enough time. So basically, this is the basic experimental setup you have. So you would have what's called an AFM tip right here. So you have this very small tip and you have the NV centers basically here, and you're giving a microwave source and you're moving it on a sample stage in order to detect a magnetic field. I'm also going to skip this because there's not enough time. But basically, the gist of it is that the NV center is the best magnetic center for room temperature and very close measurements. This is basically what this size means. So example of the applications of NV center magnetometry is basically detecting really small magnetic fields in very close situations, basically situations where you cannot touch the sample, but you need to be very close to the sample in order to sense it properly. So this is an example of Nature Communications paper in which they used the NV center to detect basically, they used the NV center to measure the current, the Josephson current in the Josephson junction. So you have this diamond tip here, and you have the NV center at the end right here, and you have this, your superconducting material, and you have tungsten in the middle to create your Josephson junction. And they used basically NV center, this magnetometry sequence, to detect the final magnetic field of sequence. So basically what they do, this is basically what I skipped, but what they do is they microwaves to rotate the Bloch sphere. So they rotate the Bloch sphere and let it drift due to the magnetic field to gain a phase. And then you rotate it again, and then you read out to get a population. And that basically tells you how much the Bloch vector rotated. And you're using this phase to indirectly calculate the magnetic field, basically. So in the interest of time, I'm glossing over the details. You can ask questions later. But basically, they use this magnetic field and they use the inverse Fourier transform to recreate the current in this case. Yeah, and you can do the same to measure very small critical fields. So basically, in this paper, they also used the NV center to measure the critical field of a type 2 superconductor. And then, so because of these very wide range applications for sensing NV centers, very versatile applications, there have been actually pushes to miniaturize these NV centers in small devices like these. And basically advances in very small scale photonics has led this to be possible. So as you can see, this is the very mini version of the experimental setup I showed earlier, but this is basically possible now. So they're basically, there's been pushes in research to find more ways to miniaturize the setup for integrations into, for example, military vehicles, medical basically, medical equipment as well. So, yeah, the section on nuclear spin is basically to explain how you can do quantum computing with NV centers. So as I mentioned earlier, we're basically your nitrogen, your vacancy, and your carbon. And then we've been primarily using the electron spin for sensing. But if you take notice, there's something called the nuclear spin. And we use this nuclear spin as basically what's called a memory qubit. So we can actually exploit the nuclear spin to store data, and the electron spin is used for reading out the data and initializing, doing operations on the nuclear spin. So if you look closely into the NV center, there are actually three components. You have a hyperfine interaction, you have a nuclear Zeeman splitting, and you have a zero field energy. So the hyperfine interaction is actually what we want to concentrate mostly on. And these are due to the interactions basically between the nuclear spin and the electron spin. So we can detect these hyperfine interactions by doing CW-ODMR again. And then the coupling to the nuclear spins is manifested basically in this ODMR spectrum. So as you actually increase the nuclear spin, it gets finer as B decreases. Now, you need to be at very low, the catch is you need to be at very low temperatures in order to actually see this very well because of the thermal noise. So as you increase the temperature, basically these peaks will get more and more broad, which is basically what you're seeing right here. So we can use this to actually create quantum computers. So we actually, what we do is we exploit the nuclear spins in order to implement 2-qubit gates. So by pulsing, as you can see on the right, this is the basically PL spectrum of the hyperfine coupling. Basically, the splitting of the energy levels due to coupling from the electron spin to that of the nuclear spins, basically. So we have two spins here, and the interactions between the electron spin, which is basically our ancilla qubit, and our memory qubits, the nitrogen and the carbon, they create this, basically this pattern right here. And by pulsing these resonant frequencies here, we can actually implement Toffoli gates, because when this electron spin is in the zero state, we don't get any operations at all. But if it's in the minus state, we get these hyperfine couplings, right? So if we initialize the electron into +1 state and we apply this microwave pulse, we're applying these gates in turn. So this is basically our Toffoli gates right here, right? So if I wanted to implement the traditional Toffoli gate, we will get -1 and 1, 1 right here. So 1, 1, and then we're applying this onto the electron, basically. So our traditional Toffoli gate right here. So by pulsing out the differences of the resonant frequencies, we can actually control the nuclear spins. And so the authors right here use this to do Bell state preparation in this paper. So yeah, by basically applying microwaves at these frequencies, you can actually implement these Toffoli gates and create Bell states. So what I said earlier, you need very low temperatures in order to see these. So this is the limitation. And this is basically what's called a strong coupling. But can you use the weak coupling? Yes, you can, apparently. You can use the weak coupling to also implement quantum computing. What you do is you use electron spin to read out and control weakly coupled nuclear spins by using their correlations in this bath of weakly coupled spins. And the delta dope diamond is actually very good for this because we have a 2D bath of very weakly spins on top of the NV center layer. So what they do is basically they perform this gate sequence, which is actually called the CPMG sequence, to actually determine what your nuclear spins are. So basically each of these peaks correspond to a separate tau, which is the delay between the pulses, and a certain n, which represents the rotation angle of your gate. So basically how many times you repeat this sequence determines the rotation angle of your 2-qubit gate. And the T represents like what sort of operation you're applying. So if you look at the Hamiltonian, which looks like this, you have a certain tau, which corresponds to this value in the Hamiltonian. And if I apply a certain tau in the gate sequence, this tau corresponds to this tau. When k is odd, I can apply a conditional gate, and k is even, I apply unconditional gate. So when my tau is basically equal to this, I perform an X rotation, and if it's not equal to this value, I perform a Z rotation. So you can use this property of the Hamiltonian to implement your 2-qubit gates, basically. But the catch is, since you can only read out the electron spin, to ensure the nuclear spin is initialized, we have to actually initialize the electron state, and then we have to swap it with the nuclear spin state, which is kind of funny. Yeah. I'm going to skip over tomography because in the interest of time. Basically, the gist is you can use this property of the nuclear spin and electron spin being coupled together to perform basically gate operations. And you can notice every time we do these operations, we need to do a swap gate. So basically, we process to entangle nucleus 1 and nucleus 2, we entangle the electron nucleus 2, and then we actually swap 0 and 1 in order to entangle them together. Yeah, and they also implement error correction here. Like this is a 3-qubit repetition code. And I'm going to actually skip this part because we've run out of time. But as you can see, there is in fact an effect of error correction and no error correction. So basically the conclusion here is that NV centers are cool. Basically, they provide a very promising spin defect platform with applications in sensing and quantum computing at room temperatures. So you can use NV centers to do all of these from 4K up to 600K, which to my knowledge, no other platform offers. And so we can also use these applications to basically culminate in the effective simulation of quantum phenomena. So thank you for listening to my talk, and I hoped it provide a wide audience with a sufficient introduction to what NV centers are and what you can do with them. Thank you. Yeah.
So thank you for your presentation. And if you have any questions, please feel free to ask them. Yeah.
Okay, I have a couple of questions. To be clear, you cannot perform computations in room temperatures with NV centers. Is that right?
You can,
You can,
actually. Yes. You
But
cannot perform the strong coupling here,
but you can do
but
weak
if
coupling.
you're, well, of course, if you have low temperatures, that's great. But if you, well, it is technically possible, but of course, when the number of envy centers increase, the noise gets too large that it becomes unviable. But if you're talking about a single envy center and which are weakly coupled to a couple of spins, you can do computation at room temperature, basically. I mean, basically quantum sensing is basically a qubit basically being utilized for sensing. So technically you can, but it's not practical. So yes, you can and you can't at the same time. Because what are you
Yes.
going to do with one qubit? What are you going to do with one qubit? Not much, right? So
Right. Yeah, speaking of a single qubit, is it possible to couple is it possible to couple two different electron spins? Like in this presentation, you talk about coupling
Yeah.
electron spins with multiple, I guess, nuclear spins, right? But is it
Yeah.
possible to couple between two electron spins? Because I guess you have to do that to perform maybe multi-qubit computations, I guess, because only having a single electron spins means that basically you have only a single readout and a single control qubit. Well, even though if you have like lots of memory qubits, that won't be really a multi-qubit computation, or is it?
Well, in theory, you can, but in practice, it's very hard. Because when you have this path of envy centers, right here, so basically, if you're at high temperatures, let's see. I showed you this graph, right? This graph becomes very broad. Basically, these peaks become very broad, which means that one frequency controls multiple spins at once, which basically, if you want to find your resonant frequency, it's so broad that you don't know which actual frequency corresponds to one frequency. So if I have envy center A, which has a different resonance frequency here, envy center B, it's supposed to have a different resonance frequency here. The problem if you have like high temperatures or even at low temperatures as well, is that this is very broad. So I don't know which frequency is A or which frequency is B, which is a problem because if I wanted to do gate operations on A and B, I would need to know their separate resonance frequencies. So it's very hard, which is why we use nuclear spins as basically data qubits, because there are a lot of them. There are a lot of them, and they're all weakly coupled to this, basically guaranteed to be weakly coupled to this. And since they're weakly coupled, I can just do this ODMR and find these peaks at low temperatures. But if I wanted to find the electron spins in here, yeah, that's very challenging, to be honest. Yeah. So in theory, you should be able to do that, but in practice, it's very difficult.
Speaking of the Pierre curve, is
Yeah.
the Pierre dip constant, or is it like a function of some parameters? What determines how
Oh,
much the
okay.
field is dipped?
I can talk about this. Like, this is actually what my research is about. So basically, what happens with a contrast dip, it's very, very strange. So for the delta doped diamond I'm currently working on, you have an intermediate regime. So basically, when you decrease the temperature, the dip gets larger, right? And then it gets smaller as if you increase the temperature. So if you increase the temperature, dip always gets smaller because of noise. But if you decrease the temperature further enough because of the spin noise actually causes the dip, which is called the contrast, to decrease. So you have actually this intermediate regime, is that if you go at very low temperatures, which are needed to do computing effectively, you actually have more noise. You actually have more noise for delta dope diamond.
And what's that
For
scale?
bulk diamond is actually the contrast just decreases, keeps decreasing. But for delta dope diamond, it has intermediate region. So yeah.
And the temperature scale for that intermediate region is how much Kelvin?
From around 100 Kelvin.
100 kelvins.
So
That's
below
actually
100 Kelvin, you get this increase in noise.
that's actually
So
very high.
yeah, so there's actually a peak of the coherence time at 100 Kelvin, and then it actually decreases after 100K. No, under 100K it decreases. Why we don't know, don't actually knows why. And there's actually no accurate measurement. So I said about 100K because there's no paper on the actual exact value. This is just what we're theorizing from the data.
And a simple question, you said that MV sensors are the best sensors in terms of because it has a wide range of temperatures and it works
Yeah.
best at like proximity distances.
Yeah.
How close is that distance? Like what's the scale?
Yeah, so this is actually the graph I skipped over. So this is MFM, magnetic force microscopy, basically a cantilever moving up and down. And this is your basic squid, and this is your NV center. And as you can see, from 10 NV centers work from 10 to the -9 all the way to 10 to the minus, basically up to here, like basically 10 to the -3, 10 to the -4, yeah. So basically, this actually shows the range in which it's functional. So for NV centers, you can do magnetometry in this entire range, basically, up
So
to
you
10 to the
can-
-9, yeah.
So you can do from millimeters to nanometers.
Yes.
But I guess in terms of like military applications, I guess you have to detect magnetic fields like much further. Like for instance, if you like to detect mines inside the ground, so maybe you have to detect magnetic fields that are like maybe much further away. So I'm just don't understand how you can do these applications in like real like military devices. I guess that's what they research in ADDs in Korea, but how do you actually do that?
You mean so for military applications,
That's
you're
right.
detecting magnetic field really far away,
Yeah,
right?
right.
Well, there are all military applications where you might need to detect a magnetic field that's very small, and then a magnetic field that may be like very close up. So for example, for detecting very small eddy currents in metals underneath the ground, that could be a military application as well. And if these eddy currents are very, very small, you might not be able to detect them with other sensors. And the selling point of NV centers is basically that you can use them for up to 600K, up to 600K. So yeah, so at very extreme temperature ranges, the NV center can be used to detect magnetic fields, basically. But yeah, of course, your concerns are valid, is that, well, maybe you need to detect the magnetic field very far away. But if they're very far away, they're very small, right? So you can still actually detect them with NV centers. But the point here is that if you get too close to a sample, for example, the cantilever is limited by the actual size of the cantilever because it can't, yeah. So you can actually get very, very, very close to the sample because it's basically an atomic sensor right here.
Up to atomic levels.
Yeah, up to atomic levels
okay.
right here without disturbing the sample itself.
Okay. And what is the minimum like sensitivity or magnetic field?
It's around nanotesla basically.
Nanotesla.
So a very interesting new research as a result from the Auschwitz lab actually came out, is that they use proteins to detect up to femtotesla. Yeah, so NV Center has a serious competitor right now, but yeah, I can't talk about the details because it's still in preparation. But they've used proteins now to detect up to femtotesla. well, picotesla room temperature, but 10K femtotesla basically.
Okay. Thank you.